Welcome to Discrete Mathematics. Today, we are going to explore a fascinating concept called order-isomorphisms. Have you ever noticed how two completely different situations can feel exactly the same underneath? In mathematics, we often find that systems with different elements and different rules actually share the exact same structural skeleton. Understanding this allows us to solve a problem once and apply it everywhere. Let us dive in and uncover how this works. Now that we know what we are looking for, let us start with an analogy. Imagine you have two different companies. Company A is in New York and Company B is in Tokyo. The names of the employees are completely different and their job titles are in different languages. However, if you look at the chain of command, meaning who bosses who around, the two companies are structurally identical. In discrete mathematics, when two sets have the exact same structural relationships, we call them isomorphic. An order isomorphism is a perfect matching where this chain of command is perfectly preserved. Building on our company analogy, in mathematics, we study sets of items that have a specific ranking or ordering. We call these partially ordered sets, or posets for short. A poset is just a collection of elements combined with a rule that tells us how to compare them. For a function to be an order isomorphism between two posets, it must do two things perfectly. First, it must be a bijection, meaning it creates a perfect one-to-one pairing between every element in the first set and the second set, with nobody left out. Second, it must preserve the ordering rules in both directions. To make this rigorous, we need a way to write it down. This formula represents the mathematical bridge we are building. The letter F represents the mathematical function or mapping itself. The symbol P stands for the first partially ordered set, which is our starting domain. The arrow indicates the direction of the mapping, taking elements from the first set and pointing them to the second set. Finally, Q represents the second partially ordered set, which is our target destination. If the size of set P increases, the mapping must expand to cover the new elements to maintain that perfect one-to-one relationship. Now that we have our bridge, we must ensure it preserves the structure. This equation is the heart of an order isomorphism. Here, x and y are any two elements chosen from the first set. The symbol less than or equal to sub p represents the specific ranking rule used in the first set. The double-headed arrow means if and only if, guaranteeing that the left side and right side always happen together. On the right side, f of x and f of y are the matched counterparts in the second set, and less than or equal to sub q is the ranking rule there. If x moves up in rank, its counterpart must also move up. Before we move on, let us see this with a concrete example. We are given a starting set P containing the numbers 1, 2, and 3, which uses the standard less than or equal to rule. We are also given a target set Q containing 10, 20, and 30 using the exact same standard rule. We are asked to prove that the mapping rule f of x equals 10 times x creates a valid order isomorphism between these two sets. To solve this, we must first verify that the mapping is a perfect one-to-one pairing and then test the order preservation rule. Let us test the bijection requirement by applying our mapping rule to each element. We begin by substituting the number 1 into our function. Multiplying 1 by 10 gives us 10, which perfectly matches the first element in set Q. Next, we substitute the number 2 into the function, giving us 20, matching the second element. Finally, we substitute 3, which gives us 30, matching the final element. Because every element in P maps to a unique element in Q and nothing is left out, we have successfully proven the bijection requirement. Now we must verify that the structural ranking is preserved. In our starting set, it is a known fact that 1 is less than or equal to 2. We look at their mapped counterparts, which are 10 and 20. Since 10 is indeed less than or equal to 20, the ranking relationship has survived the translation perfectly. We can repeat this check for every possible pair, like 2 and 3 mapping to 20 and 30. Since the order holds for all pairs, we can confidently conclude that this mapping is a true order isomorphism. The two sets are structurally identical. Now that we have used this formula on numbers, let us look at a slightly more complex, real-world applied example involving different types of rules. We are given a set of numbers that divide the number 6, called D6. The ranking rule here is divisibility. We also have a completely different set S, which is the power set of a set containing two letters, A and B. The ranking rule here is subset inclusion. We are asked to determine if the structure of divisibility among the numbers perfectly matches the structure of containment among the letter collections. We now establish a one-to-one mapping between the two sets. We pair the number 1 with the empty set, because 1 divides everything and the empty set is a subset of everything. We pair the number 2 with the set containing just A, and the number 3 with the set containing just B. Finally, we pair the number 6 with the full set containing both letters. This completes our perfect bijection, ensuring every number has a unique letter collection counterpart. We must now test if the structural rules are preserved during this translation. In our first set, the number 2 divides evenly into the number 6. We look at their mapped counterparts, the set containing A and the set containing both A and B. Since the first collection is entirely contained within the second, the structural relationship is perfectly preserved. This also works when the rule fails. 2 does not divide 3, and correspondingly, the set A is not a subset of the set B. Because the structures perfectly mirror each other, they are order isomorphic. This brings us to a visual representation. The diagram you are seeing visually proves the concept of order isomorphism in a way that equations cannot. On the left, we see the hierarchy of numbers based on divisibility forming a distinct diamond shape. The number 1 is at the bottom, branching to 2 and 3, which converge at 6. On the right, we see the hierarchy of letter collections based on subsets, forming the exact same diamond shape. Even though the elements and the rules are completely different, the geometric structure of their relationships is identical. This visual match is the ultimate proof. So, we have proven that these structures match. This brings us to an important question. Why does this concept matter in the real world? Because proving complex properties about systems is incredibly difficult and time-consuming. If a computer scientist writes a highly efficient sorting algorithm for one specific data structure, they want to know if it will work on a different data structure. Order isomorphisms act as a universal translator between different domains. If two systems are order isomorphic, any structural truth, algorithm, or theorem discovered in one system is automatically guaranteed to work in the other, saving enormous amounts of duplicated effort. To wrap up, let us review the most important ideas we have covered. An order isomorphism is a perfect structural match between two ordered sets. It requires a strict one-to-one pairing of elements that perfectly respects the ranking rules of both sets in both directions. When two sets are order isomorphic, they are identical in every structural way, differing only in the names of their elements. This powerful concept allows mathematicians and computer scientists to solve a hard problem just once and instantly apply that solution to countless other structurally identical systems. You now understand the foundation of order isomorphisms.